This is problem 44 from the magnetic field. We have a circle of radius r, and we want to find the magnetic field at the origin, and we have a current I flowing in the clockwise direction. We're going to follow the steps they outline for us in order to successfully solve the integral. And before we begin, let's just copy over the Biot-Savart law, which is what we're going to be using to solve the problem here. So we have the magnetic field is equal to mu naught over 4 pi. Then I have the integral of I ds crossed with r hat divided by r squared. So I want to carefully identify and label theta, the location of the differential element on the diagram above. I can put the differential element wherever I want, but I like to keep it in the positive, well, when x is positive and y is positive, so in the first quadrant. And then the angle here is theta. Carefully identify and label the location of the point of interest. The point of interest says at the origin. So there it is. Write an expression for ds, the vector differential element. Okay, so this is our differential element, and now it's a vector, and the vector is pointing in the direction of the current. So that's like this. Okay, do you remember back in the electric field when we had to find the vector r hat, when we had a continuous charge distribution and it was either part of a circle or a full circle, and we said whenever we had charge forming part of a circle and we were looking for the electric field at the origin, r hat, which went from the charge to the point of interest, in that case was always going to be minus cosine theta I hat minus sine theta j hat, where you have the negative signs because you're going from the charge to the point of interest. In this case, r hat is the same thing because you're going from the differential element to the point of interest, which is pointing inward. So this is our vector r, and r hat is pointing inwards towards the center. So let's redraw this. This is our vector r. This is theta. The magnitude of the vector r, which goes here, r is equal to the magnitude of the vector r. That's the radius, which is r. So that's r. So this hypotenuse has a length r. So this is r sine theta. This is r cosine theta. So the vector r is minus r cosine theta I hat minus r sine theta j hat. Divide by the magnitude, which is r, and you get the unit vector r hat. And remember that I told you if you know this, you can just write it down without having to solve for it every time, because it's always true when you're going from a point on the circle towards the center of the circle that the unit vector pointing from that point towards the center is minus cosine theta I hat minus sine theta j hat, and this works in whatever quadrant you are in. So we're going to do something similar here. When we have to write an expression for ds, we're going to do it together now, and it's going to be a little difficult, but it always works out pretty much the same. It can actually be different because your current could be going in the counterclockwise direction instead of the clockwise direction. So you do have to worry about the sign, but we're going to see how it works in this case, and then it will always be similar when you have a circle carrying current. So we have our differential element here, and it's pointing perpendicular to r hat. So I'm going to redraw this. ds is pointing this way. Actually, I'll do it like this. Okay, so we have ds going this way, and then I have the vector r, which I'm not going to label because I don't have a lot of room. But this is the vector r. Oh, these should be perpendicular to each other. So maybe use your imagination there. Okay, so this is theta. Now, if I redraw my coordinate system here, then this angle is also theta. This is 90 degrees, and from here to here is 90 degrees, and this is 90 degrees, so this angle is 90 minus theta, and this angle is theta. Maybe I should redraw this yet again. So we have our vector ds, and this angle here is theta, and I want to write ds in component form because I need to figure out the direction. So the magnitude of this vector is ds, so this side, since this angle is theta, this side would be ds times sine theta, and this would be ds times cosine theta. And then to write this vector, we're going down and to the right. So the x component is ds sine theta, that's going in the positive x direction. And then we're going down, so that's minus ds cosine theta j hat. Okay, the magnitude of the vector we said is ds. Remember we said that in the previous problem, the magnitude is always ds, and then you just have to figure out the unit vector. So ds is equal to ds times, when we pull out the ds, what we have left is sine theta I hat minus cosine theta j hat, which is a unit vector, we know, because sine squared plus cosine squared is 1. So this is a unit vector, and it's pointing in the positive I hat minus j hat direction. Okay, now when you do similar problems, you could have, this is on page 8, you could have current going in the opposite direction, in which case, when you find ds, the signs are going to change. So now it would be in the minus I hat plus j hat direction. So, and they said instead of ds, they said rd theta, which we're going to use also in just a minute. So we said in the electric field section by the arc length formula, ds is equal to rd theta. So instead of integrating with respect to s in this problem, we're going to integrate with respect to theta. So we're going to use this. And then sine theta is always the x component, but you have to put in the sign yourself. Cosine theta is always the y component when you have the current going in a circle, but you have to put in the sign yourself. And then r hat is the opposite. Now, if you look in the beginning of the book, and this is on page 5, it says, flip the x and y components of the radial vector and add the appropriate sign. So flip the components, but then you still have to figure out the sign yourself. And this gives you the tangent vector. So in this case, they're looking for t hat. But if you know r hat, which we have here, you flip the components like we did here. So sine is now x, cosine is y. But you still have to figure out the sign yourself. Now this is for finding the tangent vector, but it worked in this case because ds is pointing in the tangent direction. So if you have r hat, then you could also say, if I'm looking for ds, I know to find the unit vector for ds, I just flip the components, but you still have to figure out the signs. Okay, so that's on page 5. Or you can just remember it's going to be plus or minus sine I hat plus or minus cosine theta j hat. Okay, and then we're ready to write an integral expression. Okay, so I have my expression up here. I'm going to plug everything in. So I have mu naught over 4 pi. This is a symbolic problem, so I just leave mu naught as mu naught. I is just I. That's a constant of integration, so I can pull it outside. And then before I plug in things here, it's easier for me to do the cross product first, because then I don't have to write everything else along with it. So I want to do ds crossed with the vector r, but then for ds crossed with r hat, I have to take this and divide by the magnitude of the vector r. So ds crossed with r. ds, and this is probably going to have to go on the next line, ds is ds sine theta I hat minus cosine theta j hat crossed with r hat, which is minus cosine theta I hat minus sine theta j hat. Okay, then if I do the first term here times the first term here, that's I hat crossed with I hat, which is 0. Then if I do the outer terms, that's ds sine theta I hat crossed with minus sine theta j hat. I hat crossed with j hat is k hat, so it's ds sine theta crossed with minus sine theta, so that's minus sine squared theta I hat crossed with j hat is k hat, so that was the outer terms. Now we'll do the inner terms. So I have this ds here, so it's ds minus cosine theta crossed with minus cosine theta times minus cosine theta is plus cosine squared. So this is ds times cosine squared theta, but this is j hat crossed with I hat. So we already took care of this negative sign and this negative sign, but for j hat crossed with I hat, we get negative k hat because that's not alphabetical order, so we have the negative sign there. So that's negative ds cosine squared theta k hat. And then for the last terms, it's j hat crossed with j hat, which is 0. You can pull out the ds. We could have just left it out front when we did the cross product. And so pull out the ds, and you have minus sine squared theta, and we'll stick the k hat at the end. Well, let's pull the negative sign out here too. Okay, so this is sine squared theta plus cosine squared theta. But what is sine squared theta plus cosine squared theta? That is 1. So this is minus ds k hat. That was ds crossed with the vector r. So for ds crossed with r hat, we still have to stick the magnitude of the vector r into the denominator. But the magnitude of the vector r is just r. So we could say this over here also. ds crossed with r hat is equal to, like we said in the previous problem, ds crossed with r divided by the magnitude of the vector r, since r hat is the vector r divided by the magnitude of the vector r. So this is equal to minus ds k hat divided by r. Okay, so that goes in for what's in parentheses there. We already put the I outside, and we also have an r squared in the denominator. We also want to take the minus, the ds that we have here, and instead of integrating with respect to s, we want to integrate with respect to theta. So we're going to replace ds with r d theta. So let's do that down here. So this is minus ds, which is r d theta. So finally we get minus r over r is 1, so it's minus d theta k hat. And that is still what we had in parentheses here. So the I went outside, ds crossed with r hat is minus d theta k hat. Let's stick the negative sign out here. So that's d theta, and we'll put the k hat at the end. This is divided by little r squared. Little r is equal to capital R, which is the radius. R does not depend on theta, so that can come outside also. We still have to find the limits of integration. We're integrating around a full circle, so we start here at 0, we go all the way around the circle, and we end back here at 2 pi. So for a full circle, we go from 0 to 2 pi. The r squared can come outside, so this is minus mu naught I over 4 pi r squared. Then when we integrate d theta from 0 to 2 pi, we just get 2 pi. So this is times 2 pi k hat. And we can simplify that, and we get b is equal to minus mu naught I. 2 pi over 4 pi is 1/2, so that's 2r squared k hat. That is our final answer. And if you take a look at the problem they did at the beginning of the book, they got mu naught I over 2r. Ooh. So I actually have an r squared here where I should have an r, so we'll come back to that in a minute. So it's positive for them and it's negative for us, because in the beginning of the book, and this problem starts on page 7, and then there's page 8, which we looked at while we were solving this problem. So the current's going in the opposite direction. So if the current's going this way, then if you look up here, put your thumb this way, and in the center of the circle, your fingers would be pointing upward. As you go around the circle, your fingers are always pointing upward when you look at the center. So here, the magnetic field would be pointing out of the page in the k-hat direction. So here, if your thumb's pointing this way, at the center of the circle, your fingers would be pointing in. As you go around the circle, your fingers are always pointing in at the center. So we have the minus k-hat direction just because the current's going in the opposite direction. This I that we have in the Biot-Savart law is just the magnitude of the current. And then the direction comes from the direction of the vector ds. So ds is pointing in the direction of the current, and I is just the magnitude of the current. Okay, so now we have to figure out why I have an r squared here instead of an r, and that is because here I said I was doing ds crossed with the vector r, but I didn't actually do that. I did ds crossed with r hat. Unlike what I usually do, well, I guess I did it here. This is the vector r, but I didn't use that because I didn't put the r, and I actually did r hat. So then down here, when I divided by r, well, I wouldn't actually need to do that. Let's just cross that out. This is what you get for ds crossed with r hat, and then you just have to say ds is minus r d theta k hat. So instead of putting in a minus d theta k hat, I should have had an r up here, which would cancel out with one of those r's in the denominator. So that fixes that, and that concludes problem 44.